Welcome, and this is the lecture number 56, and we are discussing the gas based DR process, and we have already discussed the fluidized bed DR process, like we have discussed the fire process, there is a finmate process and then circuit process, and then we also started with the shaft furnace based process, and those are most popular. Even today those are existing. Unfortunately, the fluid bed reactor could not see the light of commercialization. It was initially commercialized, and then finally it has to shut down, and the productivity slowly reduced, although as I said they had very elegant process technologies, but because of some sticking problem and high pressure in the fluidized bed, they could not sustain. And then we started with the discussion with the shaft furnace based processes, and we discussed about the two process, HOL1 process, that is based on your shaft furnace but batch reactor, 4 batch reactor in series, and then HOL process also because of high energy consumption and low productivity, that also could not compete. And then HOL3 process, which was a modification over the HOL1 process, that came into picture, and that successfully produced the DRI, and such plants are also there in the whole world, all over the world, producing around 10 to more than 10 million tons per annum. Now I will just go to the HOL4 process, that is a further modification over the HOL3 process, and HOL4 is the 4th generation HOL process. That is the Mexico based company HOLSA that basically involved in developing this process. And in HOL4 process, what is the unique feature of this thing is that this reactor does not require any reformer. This is the very external reformer. This is the most unique feature of it, and the natural gas is get reformed inside the reduction unit itself by in situ reforming take place. So the reactor here act as an dual reactor, that is in situ reforming take place as well as your reduction take place. So that's why this process sometimes is also called HOL4 Zeller process. Okay, as you can find from here, there is the natural gas that is coming, and the off gas you can take. You can also use the off gas. You can take the off gas, you dehumidified the off gas. After taking out the moisture, you make it dry gas come, and then by PSA technology, you can take out the carbon dioxide. And after obviously the off gas will contain mostly, that is the CO, and that will join the natural gas, and it will enter into the humidifier. That is, you mix some amount of the steam into it because it requires some oxidizing agent to oxidize the natural gas to the CO, and there is a deform the natural gas. So some humidification is required. So that's why some humidifier is there. So there you humidify it, and then it goes to the gas heater. That is very important. There is gas heater, and there you can take partially, you can take some of the off gas, and also you add fresh fuel such that you can to supply the heat to the preheater. Okay, so then this gas preheated around 900 degrees centigrade, and finally before entering into the reactor, you can see inline oxygen injection is there. So here what you do, by inline oxygen injection, you can partially burn the methane, that is the natural gas, and generate some extra heat, such the gas is preheated to more than 1000 degrees centigrade. Okay, more than 1000 degrees centigrade, and then before entering into the reactor. So the gas enters into the reactor at a much higher temperature, around 1000 degrees centigrade. Okay, compared to 900 degrees centigrade in HOL3. Here basically enters at a little higher temperature because high temperature is required inside, because you are doing the reforming as well as reduction, and both are requires the heat endothermic process. Okay, and then otherwise it is same, it is also a high pressure reactor, and then lower is the natural gas circulation is there, the similar to this thing. So only unique feature you can find is that the self-reforming, and is self-reforming or in situ deforming, that is very important. So HOL4 process, also known as HOL4M process, because it stands for M stands for Monterrey and the Mexico, where it was first installed, and developed by HOLSA as well as Ferrosteel AG, because some technologies has also come for the Ferrosteel AG. And now natural gas is mixed with the recycled gas. As you can find, the gas is recycled. So recycled gas containing CO, that also utilized. CO and H2 may be there. That is because whatever the gas that is coming out is a mixture of CO, CO2, H2, H2O. Obviously, this gas, when it is come, you are taking the H2O, so you make the gas dry, and after you take out the CO2, whatever is remaining is CO and H2. So this CO and H2 is recycled back along with the natural gas. Okay, and after humidification, after preheating, and also online oxygen preheating, and then the gas attains around more than 1000 degrees centigrade and enters into the reactor. So the natural gas is mixed with the recycled gas, fed to the humidifier, and humidity is controlled to adjust the carbonization. So there is the humidification you can control, such that you can control the carbonization of DRI inside it also. The gas passage through a gas preheater, where the temperature is here, as I said, 900 degrees centigrade from the gas preheater, and then on inline oxygen injection, and then you can gas can be more than 1000 degrees centigrade before entering into the reduction reactor. After entering the reactor, the gas undergoes in situ reforming, forming CO2 in presence of nascent metallic iron. That is the thing. That is the, what is the catalyst? Actually, in any kind of reformer, steam reformer or the CO2 reformer, you require some kind of catalyst. Otherwise, reforming process is not a fast process. Okay, you require a catalyst, and nickel catalyst was there evidently in that case, and that nickel catalyst here. In situ reforming, it is the nascent iron that is produced that acts as a catalyst. Okay, so that basically helps into this reforming process. Now I come to some features of HOL4 process. There is a no reformer is required, as I can see. So it is called the HOL4 ZR process. That is, ZR represent the no reforming. So gas, natural gas directly enters into the reactors without any reformer, okay, and where the reforming takes place with the fresh iron. And as I said, that is the main thing. So in case of the, if you have a steam reformer and your CO2 reform nickel catalyst there, and the catalyst poisoning over time is also a problem. So you have to change the catalyst time to time, and catalyst is very costly. So that thing is that poisoning of the catalyst take place. How the poisoning take place? Either because of carbonization of the catalyst, because during the reforming process some carbon deposition will be there. There is some carbon is there a lot of, because methane is there. So source of carbon is there. So it carbonized. So catalyst get carbonized, and also this is called the poisoning, and also that is called the poisoning, basically poisoning. In case of the CO2 reforming, when the off gas is used for the reforming of natural gas, then the poisoning becomes further more, because off gas contains some dust. Even after cleaning and all this, dust is there, so dust poisoning is there. And also sulfur poisoning also may be there, because of natural gas contains some amount of sulfur may be there. So those type of different kinds of poisoning of nickel catalyst take place when we use a reformer. But in this case, when I am using the nascent iron as the reforming, so there is no question of this poisoning. Iron get carbonized obviously, but you are always getting the nascent iron because of producing, and then after that catalyzing, it goes into the lower part and then it get carbonized. So these problems are not there. So the poisoning of the catalyst and replacing the catalyst, and this process is not there. Here always you have the nascent iron that catalyzes the process, and then further you moves down and carbonized and then go out. and again nascent iron is always coming. So that is the advantage of this zero. So it involves, it cuts down the cost of the catalyst and also replacement of the catalyst. So all the cost involved is not there. So these I have talked about. Process efficiency around 87%. If you see the energy balance here, you can see the total natural gas, what is the energy carried by the natural gas, around 2.1988 gigacalorie per ton of sponge iron. And this is through the natural gas. Natural gas as fuel to the gas. Some amount of natural gas also you give to the gas preheater. So that also carries this much of energy, 0.228. So total this much of energy is input into the system, and then you get DRI of 1.815. DRI energy is this, and the DRI sensible heat is also there, 0.096. So you add up this, there is the total energy, that is the total accountable energy. And unaccountable energy, and also tail gas goes to the preheater, so it is also accountable, tail gas get, so you can take that. And only loss is there, basically evaporation loss is 0.2 and fuel gas loss is 0.087. So if you just make, and this energy, that is this divided by the total energy that is coming in, so that gives around 87% process efficiency. Is very quite high, very high process efficiency. Okay, so with this I come to the end of HYL process. This is the HYL process. Now I will come to the next, we will come to the Midrex process, the most popular gas based process. So this is the Midrex process, and you can see the Midrex process flow sheet is here. In Midrex process, the main unique feature of this process is that off gas is recycled through the reformer. That is, the off gas is used to reform the natural gas. It is not a steam reforming. Here the reforming is CO2 reforming. It is called the CO2 reforming, and that comes from the off gas. So you take out the off gas, and top gas scrubber is there. First you clean the gas, and after cleaning the gas, a part of the gas, around 40%, is directed for the heating the reformer, for supplying the heat for the in the reformer, and 60% gas moves for reforming operation. Okay, and 40% is used for generating the heat in the reformer, and 60% goes to act as a reforming agent. And then you can see process gas compressor is there. You take out the moisture, and after that the dry gas that may contain CO and CO2. Okay, CO and CO2 and H2 also, and it is mixed up with the natural gas, and then it goes to the preheater. And preheater is basically here it is the gas preheater. It is also from the off gas from the reformer. The off gas of the reformer is used to preheat the inlet gas. So natural gas along with the off gas, cleaned and dehumidified off gas, that is the CO, CO2, H2 or H2, that mixed up with the natural gas and go to the preheating system, and then this preheated gas enters into the reformer. This is the reformer, and the reformer, they get reformed, and after getting reformed, they directly goes to the furnace. A part of the gas also joins along with the fresh natural gas and put through the bottom of the furnace. I will come to this thing. So this is basically, in this section, your carbonization of the take place by the basically cracking of hydrocarbon, there is the methane, and this reducing gas directly joins here and moves up in the upper part of the shaft reactor head, is basically the reduction reactor. So here the major reduction basically take place, and and you can find there and this gas is recycled in the lower part. In the lower part, you supply the natural gas and along with the some of the reformer gas. So basically here it is used to cool the DRI as well as carbonize the DRI by cracking of the hydrocarbon or reaction. So this is the carbonization portion, and then it comes out the direct reduced iron, and you can hot briquette it, or that is you can directly use the DRI. Okay. So this is the unique process, that is the process reference. In case of the Midrex process, your off gas is used, so there is no steam reforming, that you can understand. That is the CO2 reforming is there. And this shows that the details of the shared furnace, basically the solid comes in this direction and the gases come this, and in the cooling zone you can find there is no insulated portion, because I want to cool the DRI, so there is no insulation on the surface because I want to heat to go out. And also natural gas is used, okay, for convection and take out the heat. Natural gas is used as a cooling agent and also carbonizing agent. And you can see this gas, basically the bottom gas is circulated through again from the cooling gas scrubber is there, it cleans the gas and then it take out the moisture and then again recirculated back in the lower part. Okay, so this process is there, and in the upper part is of the reactor is insulated because the heat doesn't go out, okay, and the gases move in the counter current direction and then your reduction take place. So some of the distinctive features of the Midrex is suitable for reduction of lumpures that do not decrepit it. That is very important. Some lumpures decrepit at lower temperature, 400 to 900, and this decrepitation generates a lot of fines. So too much of fine generation will be a problem. So Ispat Dolvi India operates with Midrex with 50 to 60% lumpure, highly reducible lumpure, and the SR5 Midrex unit uses 20% lumpure. So you can see in India so many plants are there, basically SR and GSW. As I said, 60% of the top gas after cleaning and quenching is passed to the reformer, and another 40% is used as a fuel for heating the reformer. Okay. So that is the oxygen carriers like from external source like steam is not required here. Hence investment or operating costs are less. And another important thing is that the reform gas that you produced, that doesn't contain, in the reform gas do not contain any moisture, because you are CO2 reforming. Natural gas is reformed by the CO2. So the reform gas do not contain moisture, so you don't require any dehumidifier. So that is the thing. Water vapor content of reforming gas is so low that it can be directly injected into the reduction furnace without quenching. This saves energy. So otherwise, if it comes from the steam reformer, you have to dehumidify it, and then you deheat it and then pass it to that thing. But here, from the reforming unit, it directly goes into, because there is no requirement of the dehumidification. And if you do the dehumidification and all this thing in the process, you lose energy, and then again some gas heater is required and then goes into that. Here, those steps are not there. Gas directly from the reforming unit goes into the reactor. Another interesting thing is that when you are carbonizing the DRI in the lower part of the furnace during the cooling part of the furnace, then also you can passivate. Basically, during decarbonation, you also passivate the DRI. As I said, the DRI is very, basically the gas based DRI are very prone to reoxidation, right, because of their structure, morphology and the structure. So you have to passivate them. How you can passivate? If you can form a very dense iron carbide layer over the pellets, reduced pellets, okay, or the DRI, if you can form a very dense, morphologically dense Fe3C, then you can protect it from atmospheric oxidation or the deoxidation. So that is done in the Midrex process, and that's why here there is the methane gas composition, there is the proportion of the methane is controlled in such a way such that it produces a very adherent and dense Fe3C layer over the DRI. So this is the reaction by which it forms Fe plus CH4 forming Fe3C plus 2H2. So that's why the Midrex DRI is passivated against reoxidation. Now more than 60% of world DRI today is produced by the Midrex route. And energy balance in the mid-rex process, if you see, that is in gigacool, all the energies and gigacalorie per ton of DRI. You can see major input natural gas comes through the energy around 2.3 that is coming in, and then for cooling gas quenching is around 0.1. So, your output is out of 230, your output is DRI of 1.69 energy, and some other losses are there like top gas quenching and the equipment and piping heat loss and the cooling gas quenching heat loss are there, seal gas 0.03 and the flue gas 0.19, and otherwise out of 2.3 gigacalorie you are getting 1.69 DRI energy, including the sensible heat of DRI. Okay. So, the process efficiency is around 73%, and specific energy consumption is decreased from 13 gigajoule per ton to 10 gigajoule. Also, initially the mid-rex was 13, now it has decreased to 10 gigajoule because of higher reduction temperature, because of off-gas preheating of the reforming, and then you can get a very high gas temperature when it is entering at high temperature. Enrichment of the reduction gas with the methane, and you can do some methane enrichment of the reduction gas, because methane is also a good reductant. So, it also, and utilization of the waste heat reformer to preheat the process gas, So, that is why, so total heat usage, effective heat utilization, and then the reduction gas use of methane basically reduced its energy from 13 gigajoule to 10 gigajoule per ton. Okay. So, this is about the mid-rex process. So, chemical analysis of the mid-rex DRI, you can see the total iron around 91 to 93. I will say that this total iron in the sponge depends on whatever you are feeding. So, if your feed material is not good, you cannot get the total iron. A total iron indicates that is the feed material gangue content is less, such that you can get around 91 to 93. So, the feed material you have to control. Okay. So, any feed you cannot give in the mid-rex. So, then you cannot get this much of total iron. Okay. The metallic iron, that is 83 to 88%, and metallization come around 92 to 95%. It depends on the process efficiency, how effectively you can reduce it. So, it depends on the process efficiency. So, 92 to 95%, carbon 1 to 4%. So, you can, in the cooling portion, you can optimize the operating parameter in such a way such that you can carburize the DRI most effectively and reaching up to 4% carbon in DRI. Sulfur is quite low, because in gas based process unlikely sulfur will be high, and then phosphorus 0.02 to 0.04, and the SiO2 is found to be high, and that basically depends on what is the gangue material you are using. From the gangue lot of SiO2 coming, so then SiO2 is high, alumina 0.5 to 1.5, CO. This is all depends on the gangue of the material, nothing much into the process, because if your raw material is good, you will get a less gangue in the DRI, or it will be there. So, mid-rex plants in India, you have JSW Dolby plant in India. It has around 1 million ton capacity. Mid-rex plant is there, and it is 2:1, that is the CO and the natural gas base, because we know in India we do not have too much of natural gas. We have some off gas. There is offshore natural gas in the Bombay High. So, our aim is always to use the other process gas like COG. COG is the coke oven gas. You know, it is rich in hydrogen. So, we can use the coke oven gas also mixed with the natural gas, and JSW Dolby use it in a ratio of 2:1. Escher steel, presently it is called the ArcelorMittal, because ArcelorMittal has taken up the Escher steel, but the Escher steel has 6 modules and total capacity with the 6.7 million ton. JSW Angul, Odisha, this is they have set up 1.8 million ton per annum in mid-rex plant, but it is very unique, this mid-rex plant, because here there is no it is not a gas based process, it is completely a coal based process. How? Basically the coal is gasified into the syngas, and then synthetic gas used into the mid-rex reactor. Okay. So basically it is Lurgi based syngas, there is the Lurgi syngas based midrex unit. So it is a coal based midrex unit, it is not a gas based midrex unit. Okay. So what is the, I am talking about the Lurgi coal gasifier. Basically it is a fixed bed type. What is this, how does this reactor look like? It is a rectangular reactor, it is a fixed bed type reactor, and here the coarse coal are charged. There is the 6 to 40 millimeter of the coal is charged from the top, and gasifying agent, some of the gasifying agent like oxygen and steam flows in the opposite direction, right. So it is a fixed bed type, you charge from the top the coal and with a size of 6 to 40 millimeter, and from the bottom you supply the gasifying agent like steam along with the oxygen, right. And then after the coal is charged, it gets dried. What happens? It gets dried and the devolatilized, it gets volatilized, and then gasify is also gasified, and the combustion also takes place. Everything takes place in the reactant. So you can utilize the complete coal. So after get drying, the volatilization also gives some reducing gas, and then you gasify completely, and then whatever the charge is left out, that is also burned. Okay. The process is carried out at 25 to 35 bar and above 1000 degrees centigrade, very high pressure and high temperature process. And the water cooled pressure vessel, it is a vessel is used as a water cooled pressure vessel, typically diameter 3 to 4 meter. You can understand at high pressure, at high temperature you are operating. So you require a water cooled pressure vessel with typical diameter 3 to 4 millimeter normally used. And then you produce the syngas, and then syngas is fed into the midrex reactor. So these are some of the reference and conclusion. So we can say the various gas based DR process are your Finmate, Circulate, HOL series and the midrex, out of which Finmate and Circulate are the fluidized bed reactor, and these are all shaft furnace based. So all the FB reactors are not in use in operation. And then HOL is a batch type reactor involving 4 reactors. It is also obsolete today because it's, as I say, it is energy intensive and also productivity is less. And then HOL process has steam reformer, all HOL process, while midrex uses off gas CO2 as an oxidizing agent in the reformer. Both the reformer use nickel catalyst, but in case of, I will just mention, in case of the midrex, one problem is there. In the reformer, that is the catalyst has to be replaced frequently, because the poisoning of the nickel catalyst with the off gas reforming is more. Okay. So as a result, nickel catalyst has to be replaced in case of the midrex. That is the replacement of the nickel catalyst in the midrex reformer is more compared to the HOL reformer, because HOL reformer is steam reformer, it does not involve any off gas. So in midrex use off gas. So in spite of cleaning and all these things, lot of dust will be there. So that dust will poison the nickel catalyst. Okay. So and the HOL4 eliminates the external reformer and introduced an in situ reforming inside the reactor using the fresh iron and the catalyst. And this is a very unique development, because if you do this in situ reforming, in that case the catalyst problem is gone totally. So you don't have to involve the cost of the catalyst and also replacement of catalyst. So anyway, so here you have a nascent iron inside the reactor and that acts as a catalyst. Okay, so the catalyst problem is gone. And also from energy point of view, since you don't have any external reformer, so you can save a lot of energy. Now, to exploit the cheap fuel resource like non-coking coal, midrex is retrofitting its process by replacing the conventional natural gas reforming. So you have just seen that is in Angul plant of JSPL, they have set up a midrex unit with the coal-based syngas. So you produce the coal-based syngas using the Lurgi technology, and then syngas is used in the midrex. So that is the gas-based reformer is not in use. So they don't have to use the separate reformer like gas-based reformer. Here The midrex unit is sustained by the coal-based syngas. So this is a new direction to utilize the non-coking coal, especially in India where we have large reserve of the non-coking coal. We can use this type of reactor. Is welcome in our country. In the gas-rich country, they can obviously use the gas-based reforming unit, but in our country where with the non-coking coal and we have very scarcity of the coking coal, we must go for this type of unit. Okay. So where you can use the syngas generated by the coal gasification. Thank you very much.